Now let's do part B. Part B asks us to find the electron's initial speed if its speed has fallen by half when it reaches the point x equals 12 centimeters. So let's do a quick sketch of this again. Here is R, here is the origin, here is point A, or I should say rather minus A. Here is B. Our electron starts here with an initial velocity v naught. So v naught is, I'll just call that the velocity at point A. And our electron ends up here with a velocity that's smaller. We'll say this is the velocity at point B, and we know it's 1/2 the velocity at point A. Our goal is to figure out the electron's initial speed. What is its speed at that point A if it's fallen by half when it reaches point B? Well, to do this, I'm remembering what I learned in my first physics class, my first mechanics class. I learned that whenever an object changes speed under the influence of a conservative force, I should consider using conservation of energy. Conservation of energy says that the change of mechanical energy, which is the change of kinetic energy of a system, plus the change of potential energy of a system, in the absence of non-conservative forces, that change of energy is equal to 0. So in other words, conservation of energy relates kinetic energy and potential energies due to conservative forces when in the absence of non-conservative forces. So in part A, we found the change of electric potential energy in our electron. Part B, we're trying to find the initial speed if we know the final speed at point B is half of the initial. So it looks like we should use conservation of energy, which says the kinetic energy at point B, which is our final kinetic energy, minus the kinetic energy at point A, plus the change of electric potential energy is equal to 0. Well, we found the change of electric potential energy. So the kinetic energy at point B is 1/2 the mass of the electron times its speed at point B squared, minus the kinetic energy at point A, which is 1/2 the mass of the electron times its speed at point A squared, plus the change of electric potential energy is equal to 0. Well, let's multiply everything by a 2 over the mass of the electron. When I do that, I get the final speed squared minus the initial speed squared is equal to plus 2 times the change of potential energy over the mass is equal to 0. Well, the final speed squared is equal to 1/2 the initial speed squared minus the initial speed squared. And I'll move the potential energy term to the other side. So this becomes 1/4 minus 1 times the final speed squared is equal to minus 2 times the change of potential energy over m. This is now minus 3/4 times the final speed squared is equal to 2 times the change of potential energy over the mass of the electron. And I forgot my minus in front of that. Now I see that if I multiply through by -1, those minuses turn to positives. And now I can write that the final speed is equal to 8 times the change of potential energy over 3 times the mass of the electron underneath the square root. Now I'm going to do one more step before I plug in numbers. I'm going to plug in the exact expression for our change of potential energy because I want to minimize rounding errors. So here, I remember that the change of electric potential energy is equal to the product of the charge of the electron, the magnitude that is, times the magnitude of the electric field, times the displacement. So that is going in my formula. It minimizes any rounding mistakes. And now I am ready to plug in values to find the speed. We have 8 times the magnitude of a charge on an electron times the magnitude of our electric field times the displacement, which we have seen that the displacement is 14 centimeters, divided by 3 times the mass of an electron, and the mass of an electron is 9.109 times 10 to the minus 31 kilograms. And this is all underneath a square root. Well, let's do a quick unit check. I see I have a coulomb and a coulomb will cancel out. And when I plug this into my calculator, I get 9.92 times 10 to the 6th. But I have to figure out the units underneath my square root because I'm left with a Newton meter per kilogram. So a Newton meter per kilogram, well, I know a Newton is equal to a kilogram meter per second squared. So I have a Newton meter, so that's a kilogram meter per second squared times a meter, divided by a kilogram. The kilograms cancel. This is a Newton meter per kilogram under a square root. So when we evaluate all of this, I see I have a meter squared per second squared under a square root. The units end up being equal to a meter per second. So we can write that the initial speed, or the speed at point A of that electron, is 9.92 times 10 to the 6th meters per second.